Hi. So thank you, Ramon, for the introduction and also inviting me to give a seminar. Okay. So the talk is on some new astrophysical signal of axion dark matter. So actually, I know that there are a lot of people at Minnesota has done important and interesting work to axion physics. So I won't talk too much about the general stuff about axion. We'll just start with a very brief overview of axion research. Okay. So what is an axion? Axion is a periodic pseudoscalar field. So it lives on a circle. So with a say period Fa. So the axion has enjoyed a wide range of phenomenological applications. So the one we're all familiar with is the Qcexia as a leading solution to a strong CP problem. So you see just a cartoon like a classical picture of a neutron. So in general, we expect the theta angle to be order 1, then there will be a large neutron electric dipole moment. But experimental data tells us actually the theta is bound to be tiny. So the one solution is to promote the theta to a dynamical field on the axion, QCD axion, that it relaxes to this minimum energy configuration with no EDM. In addition to the QCD axion solution to strong CP problems, there are many other applications. Here just show some. So the general axion-like particle ALP could also be inflaton candidates, as realized, say, in natural inflation and axion Mondrovny models, and also axion, including both QCD axion and general ALP, could be dark matter candidates. The simplest mechanism is a misalignment mechanism. And just related to some recently revived anomalies, this muon anomalous magnetic moment. So the one possible explanation is to actually have a heavy axion with mass above like 10 MeV and with coupling to the muons and also photons to explain it. Okay. So given its wide range of applications in both particle physics and cosmology, the axion actually has been a pretty hot topic these days and has received a lot of interest and interests have intensified over the years. So very roughly speaking, there are 3 broad directions of axion research which complement each other. There's a model building direction, we go beyond vanilla models, we find new mechanisms which could open a new parameter space and also point to new signals. And there has been a lot of efforts in constructing terrestrial experiments to search for like light axion, whether it's dark matter or not, Deborah, DM radio, Casper, ADMX, and so on. And last but not least, there have been a lot of interesting proposals to search for axion using astrophysical or cosmic data, either the early universe data or the late universe observables. So for the remaining of the talk, actually, I'll talk about recent work that actually falls into the 3rd category. So I want to show you a kind of novel astrophysical probe of axion dark matter, actually of the electromagnetic couplings of axion dark matter. So this is work done with Manuel Ben Abed, my former postdoc and who's now postdoc at Maryland, Chen Sun, who is currently a postdoc at Tel Aviv. Just to mention that actually near the completion of our project, we accidentally learned that actually there is another group working on the same topic at MIT and McGill. We actually coordinate with each other and have both papers come out on the same day later last year. Okay, so the coupling we're interested in is this axion photon coupling, this AFF dual coupling. A is axion, F is the field strength of U1 electromagnetism. So just following this like a popular convention, we write the coupling as just as J gamma gamma. So it's actually inversely proportional to the decay constant of the axion. So there are many possible interesting phenomena associated with this axion photon coupling. So here I'm going to talk about is the stimulated axion decays. So let's first look at the spontaneous decay. So this coupling could induce, say, axion decay into 2 photons. So let's consider axion at rest. So that these 2 photons from axion decay will go back to back due to momentum conservation, and each of them will carry energy half of the axion mass. Of course, it's for a very light axion with very small couplings, its decay rate is tiny. Okay, so we could also consider a case, the stimulated decay case, where the decay rate could be enhanced. So here we can consider an external photon source. So say emitting some photons. Say if so it could, if these external photons the energy is about half of the mass of the axion, actually you could enhance the axion decay rate. So this actually just completely analogous to the mechanism for laser. Okay, so here the decay rate will be enhanced by the large occupation number of the external photon flux. Okay, so so the idea is actually to look for to consider actually the dark matter. Our universe is axion dark matter, and we look for the stimulated decays of axion dark matter. Okay, so the first set of proposal along this line was by Caputo et al. Actually about 4 years ago. So what they propose is very simple. So we have some astrophysical objects, the source here. So it generally emits a continual photon spectrum, okay, as shown by the blue line here in this cartoon picture. So so it will along this line of sight, between the source and us here, the observer here, it could, if this photon emitted actually matches the half of the axion dark matter mass, then it could enhance the axion decay. So then, so one photon from axion decay will go back towards the source, but we could collect the other photons that travel towards us. So the signal will just, because axion dark matter to leading order is at rest. So each photon, the photon we receive will be just a very narrow bump. Okay, so it's almost monochromatic. Okay, it's the peak will be broadened a little bit due to the velocity dispersion of dark matter, but it still remains a narrow peak. So what we look for is just kind of analogous to the bump search at LHC. Just look for narrow peak on top of a continuous spectrum. Okay.
Is it, sorry, a question, is it easy to understand how the peak can actually exceed the background? Because in some sense, you need a photon from the background to induce the decay. Mm-hmm. And how do you then get more decays than you have photons in the background?
That's a good question. So usually it's actually a pretty difficult signal. It's actually, it is like a small bump on this background. So
I don't even know why it would be a bump and not be underneath. I mean, if there was some different characteristic of the decay photon, then you could pick it out. I don't know what you mean by
underneath. So you have the source photon here, and you also have this photon from axion decay. So if you don't have dark matter, you just have this. If you don't have the stimulated decays, you just have this blue spectrum, and then the axion decay photons from axion decay will add additional source on top of it.
I see. Okay.
So just a question. Are there any actually bump hunts in radio or in CMB frequencies? Because typically they just have a discrete number of frequencies they look at, and that's it, right? So they
yeah, that's right. So what actually this paper study and what we're going to follow is actually it's like a proposed search for some future radio telescopes like a Square Kilometer Array, SKA.
Mm-hmm. which
Yeah.
will have all frequency coverage. I
Yeah,
see.
you will have a wide range of frequencies, which I'll come to like later when we mention the SK. Yes, you will have a range from what 300 MeV, sorry, 300 megahertz all the way up to 15 gigahertz.
Thank you.
Okay, so but these stimulated decays will not just happen between the source and us along the line of sight. It could also happen like along the continuation of line of sight. So these source photons will just keep pass us, and they could still induce the stimulated decays of the axion dark matter on the other side, away from the source. So in this case, if it hits axion dark matter and induces decay, and one photon will actually go forward and leave us, and the other photon will actually go backwards and towards us. So this photon actually, this photon from stimulated decay of axion dark matter on the opposite side and traveling back towards us is what we call the echo photon. Okay, so what you could look for is that you actually turn your telescope around. Instead of pointing towards the source, you point away from the source, and then you try to collect these echo photons. Okay, so that again, because these echo photons, because axion dark matter to the leading order is proximally at rest, this echo photon, so just they have the energy around the half of the axial mass. So again, this will lead to lateral peak. Okay. So
if you're pointing away from the source, isn't it that the Earth itself would block the photon that stimulates the axion decay? So the O there, the observer is the Earth, right?
Yeah.
And,
so I think you're just saying that there could be some shadow here.
Yeah.
So I think actually that's a very good question. So the good thing that because we're in solar system, we are moving actually, we are moving. We are actually moving around the galactic center. So actually we will move out of because of the motion of the solar system. We actually will move out of the shadow very, very soon. So that's why the shadow won't be an issue here.
Okay, I see. Thanks.
So may I ask what's the axial mass scale you are considering here?
Oh, okay. I'll come to that, but it's about 10 to minus 6 electron volt.
Okay, yeah. So I guess related, it's about what's how large the shadow of Earth is when you are looking.
Oh yeah, it's about okay. So the shadow is about like a 1 AU or something. Okay, so that actually we estimate only takes seconds to move out of the shadow.
I see. Thanks. Yeah.
Right. Those are good questions. Okay. So one advantage of looking for the echoes instead of looking for stimulated decays from the in the direction pointing the telescope towards the source is that you have less background. Okay, of course, here is just a schematic picture. It's a little bit exaggerating. There's still backgrounds from all over the sky, but at least if we point the telescope away from the source, we won't have the background from the source. Okay, so there will be less background, but not background free. Okay, I'll comment on the background later when I talk about the signal to noise ratio.
Sorry, I have a separate question just occurred to me. To enable stimulated decay, do I need a source of a coherent photon, or I just need a large photon number density in a particular frequency?
We're just using this a large occupation number.
Okay, so those individual photons, their phase are random. They're not in phase, so it's not a coherent source. So you're saying even I have a high intensity of non-coherent photon, I could still do stimulated decay just like laser.
Let's see the.
Yeah, I think the laser, they are coherent photon, right? We know the laser not only monochromatic, but they're also in phase.
I'm not totally sure, but here the calculation is kind of standard to it's pretty standard. Like so this one thing I'll probably show is just that the enhancement really comes from the occupation number at a particular the large occupation number of the source. Where's the source?
Yeah.
What did you think about it? Okay.
Yeah. Okay. We can. Yeah. Just this is a conceptual problem. We can think about later. Thanks. Yeah.
Yeah. So actually, again, the idea of looking for this Axion echoes was first proposed about 3 years ago by.
I just 1 second. I believe it's equivalent, Zhen, to the question how it's spread over frequency. If you go to the like infinitely narrow spread, then it will be in phase locked, I think. Yeah.
So we're considering the spread is really due to the velocity dispersion of dark matter, the Axion dark matter. So that's set by the it's about order 10 to -3 like speed of light. So that's a pretty small spread.
Yeah. Yeah. Maxim, I hear your point. I think there's still a difference of NO root m, but let me think about it. Thanks.
Oh, in quantum field theory, when we specify in and out states as the number of photons at a given, momentum, do you need to also specify their phase, relative phase, or not? Or you're saying that this is not a complete information? I think it's just a mismatch of two languages. You see?
Yeah, but I think in field theory we were.
Are we missing any information in the field theory specifying in and out states this way? I'd say no.
I say yes in the collection of photons, but let me think. Okay. Yeah.
No,
yeah.
We don't, right?
And then let me think about it. Yeah. Thanks.
Because then you're telling me that the in and out states are not fully described by occupation numbers.
Okay, maybe I should just call.
Yeah. Let me think about it.
The way I think is like what Maxime talked about. You just defined by occupation number. So, okay.
I agree with your calculation, or at least as I see where you're going. Yes.
Oh,
I was skeptical initially about this Caputa paper, but Andrea kind of convinced me. But I didn't kind of expect that the occupation numbers are actually much larger than 1, but they are if you go to the
in the radio band, yes.
Yeah, if you go to the radio band, yes.
So okay, again, this idea was actually proposed first by Arthur Sikivi almost 3 years ago. So what he proposes is actually sort of terrestrial search. Their source is a very powerful laser beam. So they basically, what they're proposing is just to shoot a very powerful laser beam into the sky and then collect these echo photons. Okay, I'm not expert on this laser technology. I'm not so sure how feasible their proposal is, but it is very interesting proposal. Okay, so then later, Ghosh et al. Actually said that instead of using a man-made source like a powerful laser beam, we could actually just look for sources that already exist in the universe. So in their study, actually their source is the so-called Cygnus A radio galaxy. It is one of the most powerful constant radio sources in the sky. Okay, so this idea has been proposed. So what's new? Okay, so what we realized that this earlier 2 papers seem to miss a lot of interesting feature of this Axion echo signal. So that is, this Axion echoes is actually from the entire history of the source. So what do I mean by that? So here just again, schematic picture. So the vertical direction denotes the flow of time. So from the early time to later time. Okay. Could you see my arrow or a pointer?
Yes, we can see it.
Oh, okay, sense. So then the horizontal direction is like the direction of line of sight. Okay, so let's just consider the source like emits a sequence of pulses over time. Okay, so these are shown by this blue contours. So then the source, the photon, source photon emitted at early times will pass us like earlier and travel longer distance before induce a stimulated decay of axion dark matter. And then these echo photons shown by these red bumps will come back to us. And then the pulse emitted at later times will pass us and travel short distance and induce an echo photon. The key point here is that even though these echo photons are generated by the source photons emitted at different times, they could arrive at us at the same time. So the signal, let's say at a given time TO, is really a stack of this echo photon, generated at different locations and induced by source photons at different times. So so the upshot is that just as a signal, because the echo photon flux signal is depends on the source, depends on the source flux density. So actually, the echo photon signal is really integration over the entire history of the source. So this seems like just a little point. So, but it opens up an interesting new possibility. That is, we could have an old source that's dim today that could be barely visible. But if it was very bright in the past, it could still lead to a strong signal, could still lead to a big echo photon flux. So that's the main point we're looking for. I'm going to show you what source can do that. Of course, you already know that's supernova remnant. Okay, so but before talking about supernova remnant, let me just show you a bit about the key quantities that that determines the signal strength. So that's
excuse me, what is the distance scale that you're thinking about?
So the distance scale is talking about, so the time scale we're talking about is of order 10 to the 4 to 10 to 5 years. And the distance scale we're talking about is of order 10 kiloparsec.
Okay.
So the source is in our Milky Way. So the supernova remnant we're considering is in our Milky Way. And the distance the echo photon travels is on the scale of the furthest one is on the scale of 10 kiloparsec.
Okay.
So okay, so the key quantity for the signal is this echo flux density. Okay, so you could compute this echo flux density from the Boltzmann equation. Okay, here F gamma is photon free space density, C is the collision terms. This sort of standard calculation. So this just quickly go through it. So this D is the phase space density. M squared is the average matrix element squared. So all the F's are the phase space density. Fa is the phase space density of Axial. Then F1, F2 are the photons, two photons related. So in the parentheses, we have spontaneous decay and stimulated decay, and also the inverse process of two photons meeting the median to produce an axion. So the echo argues that two leading order axion dark matter is roughly at rest. So the central frequency is set by the axion mass. Okay, so EA is just the photon energy. Okay, so the half of the axion mass. Okay, so the frequency, the signal frequency is set by axion mass, and there is the signal will be broadened with a bandwidth delta nu, and this delta nu is actually related to a dark matter velocity dispersion. So for dark matter, a Milky Way is of order 10 to minus 3. Okay. We're always working in natural units. Okay. So that's this is a sort of standard calculation. So I'll skip the details. It's just this is a master formula we arrive at. So this is the average echo flux density averaged over the bandwidth. So there are some prefactors here. Okay, so that the most important prefactor I want to point draw attention to is just this gamma A. This is axion spontaneous decay width. So this gamma A clearly depends on axion mass and axion photon coupling. So this is how the signal depends on the fundamental parameters. That's through this mostly through this prefactor. What is more important is this integration, which I want to spend a little bit more time on. Okay. So this integration is along the continuation of line of sight. Okay. It's so since we're working in natural units, time and the distance have the same units. Okay. So we're starting from 0, just means our location, and then all the way up to half of the age of the source. Okay. It's half because that actually the echo photons have to travel over the same distance as the source photons that induce it. Okay. So then the so rho is the dark matter density along this this line of sight. And then the next important thing is that because it's stimulate decay, so the signal flux density will be is actually also proportional to the source flux density, but it's a source flux density at an earlier time. Okay, so the reason so it's so at position so the reason is that the echo photon, say the emitted at a distance x away from us. So say here, the echo photon, it was produced by the light that first passed us a time 2x away. So it has to be the source photon travel over distance x, and then the echo photon travel over same distance x to reach us now. Okay, so that's why that this argument is like the age minus 2x. Okay, so that's also just a more quantitative way to say that's the point I made earlier on, that the signal depends on the past flux of the source. So the last thing that to take into account of the absorption that that we also need to take into account of the optical depths. This tau here. This factor is actually, this exponential factor is only important if the signal is really from the Glady center, where there are a lot of like baryons and a lot of things that will absorb the photon. But for what we consider, actually the signal is always away from the Glady center. So then this optical depth is very large. So then this exponential factor just close to 1. So we don't need to worry about it. Okay, so that's a master formula. So now I mention some like more complications due to the relative motions of the source, observer, and dark matter. So the first complication I want to just mention is that the source actually moves relative to us usually, right? So here is just an illustration. Again, this is a little bit exaggeration. The actual effect is not that big, as big as this. So over time, like when the echo photons travel towards us, like the source will actually could move, say over distance like ds. So then the corresponding image, like shown by this blue blobs, actually will also be moving. So in the lag effect, that this echo image will be blurred. Okay, so one could actually estimate, given the characteristic timescale, length scale involved, could estimate the what we call this aberration angle. So this object, the orbital like velocity of this object is of order 10⁻⁻3, and for the source, we'll consider that age is of order 10 to 4 years, and we're considering the sources in our galaxy with a distance like kiloparsec away. So this aberration angle is of order 10 arc-minute. So just for comparison, we're considering the supernova, the source size is about like for the one I will show you is actually 85 arc-minute. So you could see this relative motion indeed will cause a blurry of the image, but it only gives like order 1 correction. Okay. So another effect is due to the dark matter peculiar motion. It's actually could be potentially more dangerous. So, so the source photon, like so if we don't consider the motion of dark matter, the source photon, like the echo photon, sorry, or just follow, like for instance, like follow this red dashed line and the right SNRs, okay. But because of peculiar motion of like the axion dark matter, the daughter particle, the photon, will actually depart from this original route. So, so like here, like it could, the departure determined by the departure angle is determined by the peculiar velocity. So what could happen is that, as shown in this cartoon here, that you could estimate that this echo photons will not even hit the dish, the telescope dish, if due to the peculiar motion. So the way to overcome this obstacle is actually we could enlarge the collecting solid angle to collect echo photons, like emitted nearby. For instance, like so, say we have an echo photon initially without peculiar motion will not hit the detector. So follow this dashed red line, okay, will not hit the detector. But due to peculiar motion, actually this the route it's actually will hit a detector. So we could enlarge our like collecting solid angle to include these photons from nearby, so that to keep to increase the echo photons we could receive. So we could actually, based on this schematic geometry picture, we could also estimate the solid angle we actually need in order to collect this echo photons from nearby that could hit us due to the peculiar motion of the dark matter. So it's proportional to the the velocity dispersion of dark matter sigma nu, and also so the distance travels like of the echo photon is of like on the scale of the age of the source over the or distance between the source and us. So actually, so both like the orbital motion and the peculiar velocity of dark matter is of order 10⁻³ . So this like enlarged solid angle is actually of the same order as aberration angle. So it will be an all-one correction to the source sides, but it's not like it's not a big change. Okay. So okay, so now let me talk about the source. So we all studied that's a supernova remnant. That's so it comes from the this dramatic stellar explosion. Okay, so this is what the light curve of the supernova remnant. Okay, so this shows the luminosity as a function of time elapsed from the explosion. So so the simplest light curve model, which was widely used, like you could find it in like the textbook, the radio astronomy, is this. Okay, so initially the peak luminosity after explosion, the luminosity will rises up exponentially fast. Okay, so until it reach some peak luminosity, L peak, at some peak time, T peak. And then as the supernovae expands, the luminosity start to fall down, okay, following some power law, okay. And so the first phase is called a free expansion phase, and then at some time called T transition, and then the luminosity will keep falling, but the power for the falling will change. So this is actually there are two more phases for the supernova remnants, but these are the first two phases. Actually, in these two phases, supernova is the brightest, and thus argued for our signal. It's actually it's only the brightest phase that matters. So that's why we'll only show you the first two phases. Eventually, the supernova will expand. It will be expanded so much that it will merge with the interstellar medium. Okay, so in this light curve model, there's three parameters: the peak luminosity, the peak time, and this transition time. So then the spectrum of the supernova remnants actually also follows some simple power law. The flux density of supernova remnant goes like the photon energy to some power minus alpha. Alpha is the spectral index. Okay, so there actually have been a lot of studies of supernova remnant in astronomy community. So actually, this alpha actually also has a distribution. It's actually peaked around 0.5, but has a pretty widespread. Okay, okay. So these are some basics of supernova remnants. Actually, let me say a few more words about these two first phases of supernova remnants that actually will help could help later to understand our results. So the first phase, the so-called free expansion phase. So in this phase, the shock wave after explosion, the shock wave actually expands with a radius scales like the time elapsed after explosion. So before the power law falling, what happens is that the optical depths due to the free absorption and synchrotron radiation drops over time. So that leads to the initial exponential rise. Okay, so but then it's still like as it expands enough, it still will fall the luminosity will still fall. So this phase will last about like a few hundred years. Okay, so the parametrization, like the commonly used parametrization for this phase in the literature is this. So it anchors the luminosity at a peak luminosity, L peak, and it has both exponential component to parameterize the exponential rise, initial exponential rise, and also has this power law falling, like the parameterize the immediate power law falling after the peak luminosity reached. So actually, that there have been some recent statistical study based on some about 100 young supernovae in the radio band. So this study by Beaconhorst et al. Actually puts actually bounds how big L peak and bounds the values of L peak, the peak luminosity, and T peak, the peak time when the peak luminosity reached. Okay, so so the mean value, they actually get a mean value and the standard deviation. So actually, this will play a role in understanding our results later, but I'll come back to you later. But at least the point here, just there has been study by astronomers that actually bounds on this the peak luminosity and peak time for the supernova, at least for the young ones. Okay. So then there's a second phase, the adiabatic phase. So in this phase, there's some approximate energy conservation. So the pressure behind the shock waves will push away surrounding material. So there's some both analytical and numerical estimates show that the radius here scales like different power law as time to two-phase power and could last like a few 10,000 years. So you could parameterize it in two equivalent ways by either anchoring the luminosity at the transition time or anchoring the luminosity today. The key point here is just this power law falling. The power law falling in this phase, this gamma here, is actually related to the spectral index. Okay, so in this, so there have been measurements of this Lie curves, so of this spectral index. So given spectral index, so in this for this Lie curve model, we actually know the gamma, the power law falling in the second phase. Okay, so again, a little bit more astronomy stuff. Okay. So there are actually about 300 supernova remnants have been observed and collected in the so-called green catalog. There's a different catalog, like includes age estimate for some of the supernova remnants in the green catalog. Also, I should mention that actually the supernova remnant formation rate is estimated to be about 0.02, 0.03 per year. So over time scale of the supernova lifetime, 10 to the 5 years between the explosion and its merging with the median around it, we will expect about like 2,000 to 3,000 supernova remnants in the Milky Way. So you see there's a kind of mismatch, one order magnitude mismatch here. So this deficit could be just due to the selection criteria for identifying the supernova remnant. like their criteria on surface brightness and angular size. If the supernova is not, surface brightness is low, or the angular size is too standard, that this remnant may not be identified. Okay, so now let's come to the detection part. So we're considering the radio telescope. The signal turns out to be strongest in radio band. So consider the Square Kilometer Array, SKA, the first phase. So SKA is scheduled to be constructed last year. I actually don't know whether it's the construction started due to the pandemics or not. Okay, but it covers of, okay, actually I didn't, okay, so I have, I didn't set the frequency range correct before. Okay, so actually cover two frequency range. So there's SK1 node phase, which actually covers frequency range between 50 megahertz to 350 megahertz. And then there's SK1 mid, which covers frequency range all the way up to 15.4 gigahertz. Okay. So, so we actually, so for these radio telescopes in general, actually there's two operational modes, which actually will both contribute to the detection. So the first mode is called the single dish mode. As the name suggests, it just like each telescope, you just treat each telescope in the telescope array as the unit for the detection. So the angular resolution for single dish mode is set by the diameter of the dish. Okay, so there's a small d here, which for SKA is about 15 meters. Okay, so then there is the interferometer mode. So in this mode, actually, we pair up the telescopes in this telescope array. So then, so each pair serves as like an interferometer. So in this case, angular resolution is actually set by the baseline. The baseline is just the separation of the two telescopes. So again, the angular resolution scales like the wavelength divided by the baseline. So because the baseline is larger than the diameter of the larger than dish, so that means interferometer mode will have a finer resolution. So that's the advantage of interferometer mode over single dish mode. But there's a subtlety here that for extended signal with size above this angular resolution, actually interferometer mode could not detect it. It's similar like to, so for double slit experiments, if we, instead of using a point source, if we use extended source, like larger than the, like some lambda over d, where the separation between the two slits, actually you will not see as an interference pattern. Okay. So this actually means that as frequency increases, so the angular resolution of these interferometers for given baseline will actually decrease. So then for a given like signal with a fixed size, the number of baselines contributing to the detection could actually decrease. So the interferometer mode actually will, the sensitivity actually will deteriorate at higher frequencies. So the last thing I want to mention is that actually, of course, there are usually more than one telescopes in the telescope array, like order hundreds of telescopes. So the signal to noise ratio for single dish mode will be enhanced by square root of n if there are n single dishes. Okay. For the interferometer mode, because the basic detection unit is a pair of telescopes. Size, there actually will be square root of actually about n. The signal to noise ratio will be enhanced by n if there are n telescopes in the array. So so that's another advantage of interferometer mode over single dish mode. So then the signal is the figure of merit is signal to noise ratio. The signal power is proportional to the average flux density and also proportional to the total collecting area of the telescope. Then for the noise power is actually determined by something called system noise temperature. So this is dominated actually, we don't have the background from the source when we look for the Axion Echos, as I mentioned at the beginning. So here the system noise temperature is dominated by the synchrotron background from the Milky Way or extragalactic sources. So we actually did a pretty careful job using some maps, radio maps from the astronomical missions to actually calculate the background. Okay, Now, let me.
Sorry, JiJi, what determines delta nu, the frequency band?
Oh, the frequency band. Okay, this delta nu is again set by the dark matter dark matter velocity dispersion.
Okay, we are assuming the light source. Are our light source a broadband in photon frequency, or they are very narrow in bands?
So the source like is still like emits a continuous spectrum. It's just the only frequent only for photons in the frequency range like around like the axial
matches the axiom.
Yeah. So it's basically determined by the axion dark matter.
Sure. I just want to understand that. Thanks.
Yeah. Okay. So here's the result. So we surveyed all the existing supernova remnants in the green catalog, in particular those with the ages from the other catalog. So this we find the most the supernova remnant that gives the strongest echo signal. That's this one, G39.7 / 2.0. Okay, it's not a famous one. So the constraint is shown in the axial mass and the axial photon coupling plan. Standard plan. So the gray regions are the existing bonds, like say from CAST and others experiments and observations. So for this plot I show you, so I'll talk about uncertainty in a minute. But for this plot, actually we just pick all the parameters of the supernova remnant to be the central values provided in these catalogs. Okay, and the blue contour only considers contribution from the second phase. Okay, just quickly remind you what's this adiabatic phase. Okay. While the red contour actually combines both the contribution from the second phase and also the first phase, the free expansion phase. So not surprisingly, the one we consider the brightest phase, the first phase, actually the sensitivity will be improved quite a bit. Okay, so you could see that the sensitivity actually is comparable or better compared to CAST in the range when axial mass is around the 10⁻⁶ electron volt, or the frequency around 0.1 gigahertz. Okay. So this supernova remnant, like this most promising one, is an old one. It has a lifetime between 3 × 10⁴ to 10⁵ years. It's not even among the brightest radio source today. Okay, the brightest extrasolar radio source, like around above 1 gigahertz, is also a supernova remnant, the so-called Qcexia A, but it's a young one. It only has a lifetime of 340 years. Okay, today's the Qcexia, the luminosity of Qcexia A today is about 30 times as bright as this old one. But still, this old one gives the much stronger signal, just because that like it's past it past the flux is very huge. Okay, so another small technical point is that these sensitivities for deriving sensitivities, we consider both interferometer and the single dish operational modes of the radio telescope. Actually, for low frequency, actually it's the sensitivity mostly comes from the interferometer mode. For the high frequency, it mostly comes from the single dish mode. Right. So here's a plot to understand, to help understand better why this old supernova remnant could lead to like the biggest signal. So here we show this is a busy plot. Okay, so that the two axes are the transition time, T transition, and T peak, the peak time when the peak luminosity reached. So given the light curve model I showed you earlier on, so this the light curve model has 3 parameters. So that if we fix T transition, T peak, the peak luminosity of the supernova remnant is also determined. So first set of contours I want to draw attention to are these blue contours. So these are the contours of the peak luminosity as a function of T peak and T transition. okay, in this standard units used in astronomy, And then, so then what it shows is in these shaded regions are the sensitivity to the axion photon coupling. So we fix the axion mass to be 10 to minus 60 electronvolt. So the lighter the shaded region is, the more sensitive this parameter space is to the axion photon coupling. So there are other. So then this red solid line is the central value for the T peak that derived in this statistical analysis I mentioned earlier on by Beaconhorst et al. Like these do a statistical study of about 100 young supernova, and I find that the mean value of T peak is here, okay, red solid line, and the dashed and dotted lines are the 1 sigma, 2 sigma, bands away from the mean value, okay, and then for the L peak, they also derive some ranges for the peak luminosity. So here shows in the purple contours are the 2 sigma and 3 sigma upper ends of the peak luminosity. Okay, so so for the contour plot I showed you before, we pick. So there are several things. First, you could see the sensitivities are like the contours, almost parallel to the x-axis, the transition time. In other words, when you change the transition time, the actual sensitivity doesn't change much. Okay, but if you change the T peak and L peak, the sensitivity could change a lot. So if we pick the peak time, T peak, to be 2 sigma away from its central value, okay, from this statistic study, like this shown by this star here, and we'll find that the peak luminosity is almost 3 sigma away from the central value. Of course, if you want to actually pick a peak time closer to the central value, you actually will get an even larger peak luminosity. Okay, so the message of this kind of busy plot is really just that this old supernova is an atypical bright source in the past. That's the reason that it could lead to a big signal. Okay, so now let me show you the uncertainties. So of varying other parameters. Okay, so here I just show the conservative projective sensitivity with contribution only from the second phase. So then we vary the age of this supernova remnant within its 1 sigma band provided by this supernova remnant catalog, and vary the spectral index and transition time, or vary combine all three. So these bands indicate the sensitivity, how sensitivity will change when we vary these parameters. So you could see the largest uncertainty actually comes from the spectral index. When you vary the spectral index, you vary the power law falling for the second phase. So that leads to a large uncertainty in the projected uncertainty. So that's also not surprising because the spectral index enters as a power. Okay. So lastly, so we talk about the existing old supernova remnants. So just for fun, we also consider some hypothetic supernovae that could be say discovered in the future. So here we just make up a benchmark for young bright supernovae that could be maybe detected in the future. So we pick so pick someone that close by, and then pick some a spectral index, and that's consistent with the statistical distribution of the existing supernovae remnants. And here we pick the flux density of this young bright supernovae to be comparable to the solar burst. So bright one, okay. So then show the projected sensitivity again in the same axion photon coupling, axion mass plan. So the here show single dish mode and interferometer mode, and this young supernova actually is still in the first phase, still in the free expansion phase. So we assume it's just only has a lifetime of 10 years. So you could see because in this case, like it could still potentially lead to a big signal just because that its flux is very large and it's close to us. Okay. So now let me summarize. So we'll show you like just Axion echoes from time varying sources such as Supernovae Remnant is a possible new way to probe Axion dark matter as coupling to photons. I didn't show you the bonds from like a Cygnus A, like the derived by Gauche et al. But the sensitivity is actually better than this constant source like Cygnus A. So this a strong echo signal is in the opposite direction of the source. It could be from like an old dim source, which was very bright in the past. So of course, like as I show you from the uncertainties that in order to improve the estimate, put all these sensitivities on more solid ground, we need more precise modeling of the Supernovae remnant light curves. In particular, we need to understand better like the peak luminosity and peak time, and also the spectral index. Lastly, I just want to mention a fun possibility. Imagine like just like a source, like a Supernovae remnant that expands so much, like it's so dim today that you could not observe it. Okay, but it was very bright in the past, so it could still lead to a very strong radio light signal. But then we look above the astrophysical background. So if you see a radio like a line signal above the astrophysical background, but we cannot see any bright source in either direction along the line of sight. So that may suggest one possible explanation, just that's a ghost source. That's a source that was very bright in the past, but now it became a ghost. So of course, that you think of this could also be like you could reverse it as use this to find the old supernova remnant. So it's sort of a way to do supernova remnant archaeology. Okay, so that's what I want to talk about. So thank you for attention.
Thanks a lot for the next talk. Let's thank JiJi. Any questions from the audience?
So I have a question about this. You mentioned this Qcexia proposal as well.
Yeah.
And is that covering the same parameter space that you're covering as well? This powerful laser.
I think it's similar. Like I think it's also in the radio band. Okay. I don't quite remember like how far it will go because so in their study they also actually so for the results I show you, like we assume Axion dark matter like density distribution to be like the standard FW profile. But for their studies, they actually considers like some more concentrated like Axion dark matter density profile. That's the profile actually Qcexia likes to advocate. So in that case, their signal actually could be stronger just because like their dark matter density could be Axion dark matter density is higher.
I see. So they could get stronger limits.
Yeah, so they claim they could get, if I remember correctly, the paper claims they could get even close to the QCD9.
I see. But that experiment is not funded, right? I mean, but
I haven't heard any follow up of that.
But it should be easy to get funding, right? Because you're shooting powerful lasers up at the sky.
I'm not sure. Like, okay, I'm not an expert on this.
No, it's like a Star Wars thing, right?
Yeah, exactly. So
the Department of Defense could give them some funding, maybe.
Okay, as I said, I do not know. Like, so we talk about like laser beam 10 megawatt year energy. I'm not sure whether that's feasible or not, but certainly, yes, I said that's like a Star Wars, like that Star Wars.
Yeah, I see. Okay, thank you.
But I don't know that you actually get constraints from this, right? If you see something, then you're learning a lot. But in terms of actually constraining things, there's all the other uncertainties, right, that you have to fold in. So I'm not sure how you actually end up with a constraint.
So just said that like we do take into account all the astrophysical backgrounds, like so again it's just that astrophysical backgrounds, and it just like calculate signal to noise ratio. So So all the backgrounds, like there has been like all these surveys of the the radio maps of the sky. So so that's already folded in the estimate of the signal to noise ratio.
Okay. And so
So
you're saying that's enough information about the sources that can give you.
So yes, they are doing okay. So indeed, like there are uncertainties, quite big uncertainties associated with supernova remnant, as shown here. Like there's some like from all these existing observations of supernova remnant, like for each one that there is like a like measurement of the radial light curve. We know the range of this the spectral index and so on. So indeed, we'll as I said, maybe that's I would say like it's following the standard procedure. We do get like this band, like so there is so the uncertainty is already taken into that. So yes, it could be improved if like if we could understand supernova remnant better. In particular, like I said here, if we like could have a better measurement of the spectral index, from like measuring the light curves, then this the bands like the bands could be shrinked, and the band could be improved. But I think it's still like just a standard procedure, like to set the bonds. It's just you need to take into account all kinds of astrophysical uncertainties.
Okay.
Sorry, related question. I'll go back to your formula for SNR just to make sure what the background. Yeah. So do you only consider the thermal noise, or you actually consider, you know, in a particular patch of the sky there are some, you know, ambient photons flying around? Yeah.
So this like so this is just so this noise actually have multiple contributions. So there's
so it's the effective temperature of the
effective temperature. So there is like CMB contribution. There's also just the device itself has a temperature. So then there is this like just a synchrotron background, like also that already takes also counts all kinds of emissions in the sky. So there is direct measurements like of the particular frequencies of the like radio maps actually that's already provided in the by the astronomers.
Okay. Yeah. By the way, just regarding my earlier question about the stimulated decay, I'm happy now. It's N, and the maximum argument is nice. So yeah, that's fine. Yeah. Thanks, Maxime, for the argument.
Yeah, this topic comes often, right? And I think it's just a mismatch of classical language and quantum language. But when you calculate things by occupation number, I think you.
Yeah. Occupation number, I think that's the same scaling. Right? There's different viewpoint, but I think
Right.
that would work.
JiJi, so I have some question about whether you have thought about applying this interesting mechanism here to, for example, detect axion radiation, axion dark radiation. So in addition to axion dark matter, people know axions can be produced relativistically. So I suspect that in that case, because it's axion dark radiation and it has been there throughout the evolution of the universe. So any bright sources throughout the whole history of the universe should be able to convert the axion or to stimulate the axion decay. Would you be able to use that?
That's a good question. So, but that's relativistic axions, right? So
yeah.
I'm just wondering whether you could still get something like a line or something like that.
There wouldn't be a monochromatic one, so you wouldn't stand out of the background, right? You would just have a broad axis. It's really hard to tell.
But what if you have a axion source that's almost monochromatic by itself? Like if you produce the axions with a specific momentum, and that's actually known to exist. I mean, so there are known production mechanisms for those kind of.
So which one are you talking about?
For example, in the early universe, there could be some parametric resonance production of axions.
Okay, fair enough.
Yeah.
Fair enough.
In that case, then the axion has a very sharp peak in the momentum spectrum. Yeah, I just wonder if you'll be able to get this stimulated decay also from the sharp spectrum of the axion radiation.
Yeah, that's yeah. Okay, so actually, I don't know, because but one thing that maybe a quick estimate is because it certainly signal depends on the so for this here, that depends on the axion dark matter density. So so then you still need to get some density, right? That's actually comparable to the at least the dark matter density. So I think that's probably for the dark radiation you talk about, I would think for the axion radiation you talk about, I would think it's probably because the bond on the it's probably not dense enough.
I see. Okay, thanks. Other questions?
So if I want to ask a pictorial question like the following, let's suppose axion is a given mass, and I do observe an excess of that particular frequency, right? When I try to look into that frequency band, how would it appear on the sky? Does it appear in a particular dark patch? There's a small, faint light source to me.
So of course, it probably not. It's radio band. You do not see it.
Yeah, sure. Let's say if we see it, okay, what's about the shocking form? Yeah.
So you will see okay, first in terms of the spectrum, it looks like a lateral peak, and then
so
in terms of the
that frequency. Yeah.
In a position, it's really okay. You should say we see is kind of a kind of bright spot in the radio band. On the opposite side, it should be the most ideal case. In the opposite side, you should also see the source. You see an object right there. You kind of you should have this
you have a pair, but I suspect that the signal I'm observing is going to be very extended due to this whole history of conversion and dispersion.
No, so I said the image size. Okay, so this in the radio band, the image the angular size is is basically you have to take into account the source size, and also mentioned this aberration angle and the large collecting solid angle due to the I mentioned earlier maybe this all kinds of these things. So this is the exaggeration, but I think the size here is about 1 to 2 degrees.
Okay.
In style.
I see. Thanks. Yeah.
Okay. Any other questions from the audience? If not, let's thank the speaker again. Let's thank JiJi.
Thanks, JiJi.
Yeah, hope everyone stay healthy, and happy. So yeah, so hope to see you in person sometime soon.